Okay, so I hope I'm audible. Let me just check a few things before I start. Okay, so the video seems to be working and the audio seems to be working as well. All right, so let's begin today's lecture. So today let's go back to the new ideas that we were discussing, mainly related to orthogonality and orthogonal subspaces and how they relate with each other and how they relate to the ideas that we've been doing so far. And so just as a little recap, the last thing that we did was we actually showed that we did a little proof and we were talking about orthogonal complements, right? Complements. And the idea was that a orthogonal complement includes every vector that is orthogonal to, so let's say if I'm talking about S complement, then it contains of every vector x such that x transpose y, that is, if you take the scalar product of x with y, you get 0, and this shows that x is orthogonal vector to y such that for all y that are in S, so this S will contain every possible vector that has a 0 scalar product with every other vector in S. Okay, so those are orthogonal complements, and we discussed a few of those, such that for example, we showed that the range of A, that is the column space of A, is actually orthogonal to the null space of A transpose, right? So it's orthogonal. If you want a subspace that is orthogonal to this space, that's the column space. And similarly, we knew that the space that is orthogonal to the column space of rho transpose, then that's just the null space of A, right? And these you can interchange. And so the idea is, we did another theorem last time around which said, just recapping this, so the idea was that if we have S as a subspace of the n-dimensional real space, then you have this interesting thing where n is actually equals to the dimensions of S plus the dimensions of its complement, orthogonal complement. So you take the space, you take the dimensions of the space, and you take the dimensions of the space, and it will give you n. And in fact, if we said that if x1 to ... xr is a basis for S, and x1 xr plus 1 to xn, so I've ensured that there's a total of n vectors here, so that we have an n-dimensional real space, and we said that if this is a basis for orthogonal complement of S, then if we combine this set of vectors, these two set of vectors, and we put them together in a single collection, x1 ... xr, then xr plus 1 ... xn, then thus this collection of n vectors is a basis for Rn. Okay, so in a way the idea is as follows. So if you have Rn, let's suppose you have this Rn, you're able to find some subspace for which you have a basis x1 to xr, and you have another basis, you have another orthogonal complement, S complement, and this one has basis xr to xr plus xn, xr plus 1 to xn, when you combine these two, when you put these two collections together, you get the entire n-dimensional real space. Okay, so that's the idea. Yes, Murtaza, we know r to the n is not bounded or rounded. It's just a visual expression. So that's fine. We're just visually describing it. That's fine. Okay. And so let's go one step further and talk about another theorem, and let's just define a concept. Let's define the idea of a direct sum. And the concept is as follows. The concept is that if, let's suppose, we have let W, small w, be an element of the vector space capital W, and such that W can be written as the sum of two vectors, let's say y plus z, where y is an element of a vector space V, which is of course probably a subspace of this original space, and let z be an element of the subspace U. Then we say, so such that and this is true for all W, for all small w's in W. So we take any vectors. So the idea is that if you can take any vector in capital W and you can write it as a sum of y plus z, where this y belongs to V and this z belongs to U, then we say that W is a direct sum of U and V, and we express it like this, that W is equals to V direct sum U, not W, sorry, so V plus U. But this is actually a sum of vector spaces. This is not one vector, this is not one vector. The idea is that this statement is actually saying, that every vector in W can be written as a sum of some vector in V plus some vector in U. And that's the idea behind the direct sum. And the reason we have this definition is to then take this one step forward, the idea that we had previously, that the dimensions of S and dimensions of the orthogonal complement of S actually is equals to n. This gives us a sense that if we combine these two subspaces, then we will get the entire n-dimensional real space. And that's exactly what we have. And so we have a theorem that says, let S be a subspace of the n-dimensional real space, then R to the n is actually a direct sum of S and its orthogonal complement. That is, you take any vector in R to the n, that is the n-dimensional real space, and you can write it as a direct sum of S and its orthogonal complement. And actually this is a unique sum, right? So this uniquely as a sum of some vector in this and some vector in this. And so let's go ahead and prove that idea. And the way we prove this is simple. We already have done a proof for the previous theorem, so if you don't recall it, I would recommend that you go through the proof that we did in the last video that was related to this topic, and where we proved that that this is a basis for R to the n, and that's why I mentioned it again. So let's go ahead and prove this. So we want to prove that r to the n is actually a direct sum of s plus some orthogonal complement. Okay, so let's assume we have a basis x1 to xr for s, so we have basis for s, and we have a basis xr plus 1 dot 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 xn for s complement. Now since we have this, we know by the previous theorem that x1 dot 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 xn is a basis for Rn, which means if I take any vector x such that it belongs to the n-dimensional real space, then x is simply can be written as alpha 1 x1 plus alpha 2 x2 and dot 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 alpha n xn. Okay, and so let's take the terms separately, and so let's say alpha 1 x1 plus dot 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 alpha r xr. Let's separate the first r terms, and then alpha r plus 1 xr plus 1, and then remaining n minus r terms, so alpha n xn. So now all of these vectors, this collection, by the way, this collection is in my subspace S because it's contained of a linear combination of the vectors which were a basis for S. So this vector belongs entirely in the space S, and this vector, because it's made up of the linear combination of the basis for the orthogonal complement, then this belongs to S, the orthogonal complement of S. And so I can say that X is simply U plus V, where U belongs to S and V belongs to the orthogonal complement of S. Okay. Alright, so this belongs to the orthogonal complement of S. And now we have one more thing to show, that this is actually a unique representation for X. By unique I mean you can't just take any other vector in S and any other vector in V and still get that vector plus that vector to be equal to X. So for example, I want to prove that this is unique, so let's say that X by contradiction, so I'm proving by proof by contradiction. Let's take the contradiction such that X is equals to Y plus Z, right, where Y belongs to S and Z belongs to orthogonal complement. So I'm claiming that this is not a unique representation. I can have another representation, but that representation gets me to U plus V equals to X to equals to Y plus Z. That is, I am asserting that U plus V is equals to Y plus Z, and I can take these terms to the other side, and on the left side I have U minus Y, and on the right hand side I have Z minus V. Now notice that U belongs to S, V belongs and Y belongs to S. That means both of these vectors are in S, which means their subtraction or their sum is going to be in S as well. This is just a linear combination of two vectors that were in S. And similarly, this is a linear combination of two vectors which were in the orthogonal complement. So we have two vectors which are equal to each other, but they are in different spaces. So what we're actually saying is that this vector U minus Y is in S, but it's also in the orthogonal complement of S. And similarly, we are saying that Z minus V is in S, because of course these two are equal, so they have to be in both of them. So this also belongs to the orthogonal complement of S. And at this point we can bring in a nice little fact. We know that the orthogonal complement, the intersection of two orthogonal complements, these spaces, is going to be just the null vector. These spaces have nothing in common, they only have the trivial zero vector in common, which means what it gives you is that U minus V, U minus Y has to be the zero vector, which means of course that U has to be equals to Y by the axioms of having vector spaces, right? And similarly, Z minus V has to be equals to the zero vector, which means Z must be equals to V. And therefore, indeed, we've shown that this is a unique representation that if you try to make another representation, it will turn out it was actually the same representation that you started off with, right? So that gives you a nice little proof that if you have another vector space Rn, if you have a vector space n-dimensional real space, you can just write it as a sum of two subspaces. So in a sense, these are just two parts of a, if you think about it, what you're essentially doing is you have a space, a subspace of Rn, so this space, and you have another subspace. So these two are orthogonal complements of each other, and so this is, so let's say this is S, and this is on the other hand orthogonal complement. Now both of these, if you take them separately, they can't span Rn because one of them has dimension R, the other has dimension n minus R, but if you combine them, if you take linear combinations of both of these, then you will essentially cover the entire space Rn. That is, any vector over here can be written as, this Rn is just a sum of, if you combine them together, take a direct sum, then you will get the entire n-dimensional real space. Okay. All right. Okay, so let's add a couple of corollaries and theorems here, which I'm not going to prove, but just so that we have for completeness. So if you have that, if actually let's just state it simply, that the orthogonal complement of the orthogonal complement, so if you're taking the orthogonal complement of the orthogonal complement, that just gives you the original space. So the orthogonal complement of the orthogonal complement is S. So essentially what we're saying is that this is the orthogonal complement of S, but we're also saying that S is the orthogonal complement of S. All right, that's a simple enough theorem to prove, and you can look at it on your own. You could try to prove it, or you could go through the book and see the proof. The next theorem is something that we're perhaps more interested in because it relates to linear systems, right? And at this point, let me just remind you what we have. We have some nice little ideas. So if you have an A, which is a matrix, an M by N matrix, then we've gone through some of the subspaces of A, and we've shown that actually that the row space or the column space of A transpose is actually the orthogonal complement of the null space of A, as well as you have the null space of A transpose being the orthogonal complement of the column space of A, right? So you can view this as the row space of A or the column space of A transpose. You can view this as the row space of A transpose or the column space of A. These are all issues that we've discussed in the previous videos, and if you want to check them out, I recommend that you do so. Okay, but the idea that we want to discuss today, we have a nice little theorem that says if A is an M by N matrix, and B is a member of Rm, sorry, not Rm, Rm. Just put a line here, hopefully it straightens out. Yes. Okay, so if we have an M by N matrix, then either you have some x in Rn such that Ax is equals to B, that is, this equation has a solution x, or there is some y in our M, such that A transpose y is equals to 0. And again, I'm not going to go through the proof of this, but let's just think about what this is actually saying, and the book represents this nicely as a. So here's the thing. The idea is that let's suppose this is my Rn, right? R M space, and if you recall that A is just a bridge, this matrix A is a bridge from the n-dimensional real space to the m-dimensional real space, right? And so A will take this, whatever vectors are here, and it will map it on to what we call the column space of A, right? So let's suppose this is the column space of A. This is the column space of A, which we write like this. So here's the idea. If B is in this entire space, then it's possible. The first possibility is that B is in this space, this column space of A, in which case so if B is in this space, then you know that Ax equals to B, there must have been some x which have been mapped onto this B. So Ax equals to B has a solution, right? If that's a possibility. The other possibility is if B, let's suppose B is not in part of the column space, that is, this column space doesn't span the entire m-dimensional real space, so B was, let's suppose, outside it, something like this perhaps, right? So you can show that this is perhaps something what it looks like. It was coming out of this plane, sort of. Plane is a visual representation, it's not actually a plane, but I'm just trying to illustrate that this B is outside this column space. And if that's true, that means this tells me that actually this column space does not entirely span Rm. Now, if you recall, you would remember that the null space and let me just make sure that my notations are fine. Okay, yeah. And so remember that if this B vector is not within this space, then recall that I can write this m-dimensional space as a direct sum of this row space, this column space of A, plus I can take its orthogonal complement. So by the theorem that I have before, you can take a subspace, add it to its orthogonal complement, and you will get the rest of the space, right? And so any vector in this space can be written as a direct sum of the column space of A and the orthogonal complement of the column space. And this is where we insert this important fact that actually the column space of A is nothing but the null space of A transpose, which means if B is not within this column space of A, it has to be, then B belongs to, that is, perhaps B can be written as some vector in this and some vector in this. So what we have is that the null space of A transpose is not empty. That's what we're getting out of this visual representation, that there are some vectors outside the column space of A. And if the null space of A transpose is not empty, that of course that there is some y in the null space of A transpose, there is some vector y such that if I multiply A transpose with y, I get the 0 vector. And of course y then must belong because A is an m by n matrix, then A transpose is an n by m matrix, then y is an m-dimensional vector. So there must be some vector y, something like this, coming exactly orthogonal in a way to this entire plane, such that we have A transpose y equals 0. So what we're essentially saying that the null space of A transpose is not empty, right? Or rather not it just doesn't contain it contains non-trivial vectors. That's the zero vector is not the only solution to the homogeneous equation, right? And that's an interesting thing to come up with. So we've basically converted it into two possibilities. So you either have a solution, or you're essentially saying that if you have a linear system, then either you will have a solution to that system, or you will have a non-trivial solution to your homogeneous equation, which essentially ties into everything that we've discussed before about linear systems and with homogeneous equations, right? Okay. Okay, so let's just cap off this class by doing an example. And so let's do an example. So let's suppose we have a matrix A such that A is 1, 1, 2, 0, 1, 1 and 1, 3, 4. So we have a 3 by 3 matrix, and let's suppose we have to find the column space of A, the null space of A, the column space of A transpose, and the null space of A transpose, right? Let's say we have to find these four sort of fundamental spaces from this, right? You can also consider this just by the way, just as a recap, this is the column space of A transpose, but also the row space of A, okay? And so the first thing to notice is that you can just reduce to row echelon form. If you reduce this matrix to row echelon form, you get 1, 0, 1, 0. This is just an example that I'm picking out from the book. And so once you have these, once you've reduced these to the row echelon form, you immediately get two things. The first thing that you get is that the row space. The row space that you get from this is, of course, 1, 0, 1 transpose and 0, 1, 1. These are the basis vectors for the row space. So any vector, so if X belongs to the row space, and row space is of course the column space of A transpose, so, or in other words the row space of A, then X is simply alpha times 1, 0, 1 transpose plus beta times 0, 1, 1 transpose, right? So that's the basis for the row space, right? And the next thing is, let's find a basis for the null space, and finding a basis for the null space is again easy once you have the row echelon form. So once you have the row echelon form, you know that 1, 0, 1, 0, 1, 1, 0, 0, 0, you're solving this equation, the homogeneous equation equals to 0, 0, 0. So what this gives us is x1 plus x3 equals 0. The second one tells us that x2 plus x3 gives me 0, which means now this column does not have a leading one, so I can consider x3 to be a free variable. So x3 is free, and now I can solve these equations. So the first equation is that x1 equals to minus x3. The second equation tells me that x2 equals to minus x3. And so if x belongs to the null space of A, then x looks like this. The first entry is minus x3, the second entry is minus x3, the third entry is x3, which essentially can be written as x3 minus 1 and 1. So, and you can convert this into, this x3 is just some scalar coefficient, right? So this is some alpha, beta, whatever. So any x that belongs in the null space is simply alpha times minus 1 and 1. And this is the null space of A, right? So this is the null space of A. So the row echelon form of A gives us basis for the null space of A and the column space of A transpose, and in other words the row space of A, right? So we have a basis. Now if you want, you can revert this logic, right? If you want the null space of A transpose and the column space of A, all you need to find is the reduced echelon form of A transpose, and that will gives us the basis for this, following the same procedure that I've done. But before you follow that same procedure, you take the transpose of A, and then you find the null space of A transpose and the column space of A, right? And I'm not going to go ahead and do these for you, you can do this yourself, but the idea is the same, that to find the row space, reduce it to row echelon form, and the non-zero rows give you a basis for your row space. And if you want to find the null space, then you just solve this homogeneous system x1, x2, x3 and express it, right? Just a small little verification. Notice that we had vectors in our row space of A, and these vectors were 1 0 1. These vectors were 1 0 1, and another vector was 0 1 1 0 1 1, and the null space of A had vector -1 -1 and 1. And so let's try to take this. Let's say this is U, V and W. So let's take U transpose V. So all of these are transpose. These are actually column vectors which I have written as rows. And so if I take the dot product of UT and W, then what we have, the dot product of U and W gives me actually, so 1 dot -1, so first entry times first entry, plus 0 times -1, plus 1 times 1, which gives me -1 plus 0 plus 1, which gives me 0. That is, this vector is orthogonal to this vector, which makes sense, that because this is part of the null space of A, this is part of the column space of A transpose. These spaces, these entire spaces are orthogonal to each other, orthogonal complements of each other, which means their vectors which make up their bases must be orthogonal to each other as well. Similarly, you can verify that V transpose W should give you 0 as well. So 0 times -1 plus 1 times -1 plus 1 times 1. 0 minus 1 plus 1 gives you 0. And that sort of establishes our confidence in the method that this is perhaps this is correct because we found vectors which are orthogonal to each other, which makes sense, right? So the verification checks out and everything seems to be going exactly as planned, right? So the method seems to work. So that's it for section 5.2. These were the remaining things. These orthogonal complements actually have a pretty nice application in least squares, in the least squares problem. And not only the linear least squares problem, where if you recall what you do in a least squares problem is you have a bunch of points and you want to fit a line through them. That's the linear least squares problem. But there's also a non-linear least square problem. For example, if you have a set of points which is non-linear and you want to fit a curve through them, then this is the non-linear least squares problem, that you want the distance of this curve from these points to be as little as possible, right? So you want to minimize this distance, the sum squares of distance, and that problem has a pretty nice solution based on these orthogonal complements, and we will go through that in the next video on Wednesday. Okay, all right.